Okay, so for this one, we're going to talk about liquids and solutions, which is something that you can make with liquids and solids, and liquids and liquids, and liquids and gases. So to start out, right, just the basics of liquid, we'll review these definitions here: vapor pressure and boiling point. So vapor pressure, the pressure above a liquid caused by evaporating molecules. Vapor pressure of a liquid increases as the temperature increases. And then we have boiling point, and that is the point at which the vapor pressure of a liquid is equal to atmospheric pressure, right? So the temperature has been increased of the liquid to the point where its vapor pressure is equal to the surrounding atmospheric pressure. And so then some things to think about for solutions, right? There are some forces that we take into account when we talk about solutions. One are the solute-solute interactions. And these are the forces that occur between solute particles that have to be overcome to solvate the solid or your solute, all right, whatever you're dissolving in your solvent. You also have solvent-solvent interactions, and these are, of course, the forces that occur between solvent particles that have to be overcome to form a solution, right, so that it will interact with the solute. And then you have your solute-solvent interactions, and that is what occurs between a solvent and solute in a solution, right? And so some of those might be some intermolecular forces. And then some definitions of some solutions, right? We have three types of solutions, one of them being saturated, and this is where the maximum amount of a solute has been dissolved in a solution, and if more solute is added, it will not dissolve, it will remain as a solid. And then you, of course, have your unsaturated, which is where the maximum amount of solute has not yet been met, and so more solute can be dissolved in the solution. And then you have a supersaturated, where more than the maximum amount of solute has been dissolved in a solution. So as it says here, this is often achieved by heating a solvent to dissolve a larger amount of solute and then cooling the solution slowly. So let's fix some things here of solute and then cooling the solution slowly. Great. Okay, so things that affect solubility. The first one, temperature. For most solid solutes, increasing the temperature of the solution increases their solubility. I say most because that's not always the case, but for most things that are solid solutes, it is. For most gases, however, increasing the temperature decreases the solubility. So gases become less soluble as the temperature increases. Solids become more soluble as the temperature increases. Now, for pressure, as the pressure increases over a solution, the solubility of a gas increases in the solution. However, pressure has basically no effect on the solubility of solids. So if you're dissolving solids, pressure does not matter. So now, the identity of the solute and solvent, those are going to be important as well. Hopefully you remember the like dissolves like rule, where polar solvents dissolve polar solutes better, and nonpolar solvents dissolve nonpolar solutes better. Also, your solubility rules that you need to memorize, right? And as it says, if you don't remember those, check page 125. There's a whole list of them, and you will need to memorize those. So those are the things that affect how soluble something is going to be, right? Temperature, pressure, and the identity of the solute and solvent. So now we're going to talk about some colligative properties, specifically two things, right? One, the first being Raoult's law, and this deals with the vapor pressure of a solvent and how it is proportional to the concentration or mole fraction of solvent in the solution, right? Where here P is pressure and X is mole fraction. If you remember, we talked about mole fraction previously, and and hopefully you know what pressure is. We'll discuss pressure much more when we talk about gas laws in the not too distant future. But that's a pretty easy one, right? You just multiply the mole fraction by the pressure of the pure solvent, and you get the pressure of your solution. Now, freezing point and boiling point depression. So this is when a solute is dissolved in a solution, both the freezing point and boiling point are affected. Freezing point is lowered, therefore freezing point depression, right? The freezing point is depressed. And the boiling point is raised or elevated. And there is an equation that goes with this, delta T equals negative I K M, where delta T, change in temperature, M is molality, remember that, that is moles of solute per kilogram of solvent, right? So it is not molarity, but molality, be careful on this one. K sub B or K sub F are the molal constants for boiling point elevation or freezing point depression. And then the Van't Hoff factor, which basically equates to the number of particles a solute will form when dissolved. So for some examples on that, sodium chloride, right, it will dissolve into 2 particles, therefore its Van't Hoff factor is 2. Something like calcium chloride, right, that has a Van't Hoff factor of 3, right, because you've got 1 calcium, 2 chlorides, and then something like glucose, C6H12O6. Remember that this is not ionic. It is covalent, so its Van't Hoff factor is 1 because this whole molecule stays together in solution. So be careful when you're looking at things like that for Van't Hoff factor. And then example time, right? So we can look at this. What is the new freezing point of a solution of water and calcium chloride? That is 0.72 molal. So we have looked up our freezing point depression constant in the book. There is a table of them in there. And I have given you the molality. So essentially, we have delta T equals I, which for calcium chloride, we just said was 3. We have our freezing point depression constant, 1.86 Celsius per molal, and we have our molality. And if we do this math, which I'm about to do very quickly here, we get 4.02 degrees Celsius. Now, that is the change in temperature, right? It's going to drop by 4.02 Celsius. So now, the next part, we all know what the freezing point of water is, right? 0. And so from that, we subtract Celsius. So the new freezing point of water, 4.02 degrees Celsius. Right, so that lowers the freezing point of water by 4 degrees Celsius. So now water will freeze at below 0. So that is the basics of some solutions and just a little bit about vapor pressure and boiling point. And I will see you in class.